Perfect. So this is the clamp that Prusa is using. And their system actually, from what I've been able to see and decipher, it's pretty simple. But the tolerances required to actually make it work, or the smoothness that is required to actually make it work, you could do it in 3D printing, but for my purpose, it kind of is a huge redesign for me. So that is why I'm not kind of trying to do it now. So let me kind of, you've seen the tool chain sequence on Prusa, right? Or should we play a video here to kind of just show what happens here? Second.
Yeah, I think you linked a video and I remember watching it, but it wouldn't hurt to play it for everyone. Just going to watch the recording.
So actually see it goes in laterally, stops there, and then it kind of just moves a bit to the side in order to release the clamp. Then it goes to the next tool head and again moves to the opposite side to actually clamp the new tool back in, and then take it out. So if I was to talk about the differences between this and the servo design that I currently have, mine will do the locking mechanism in a very similar way. Pretty much everything is the same with Daksh as well, where you actually go in, you spark the tool, and then there's a servo that activates, that opens up the clamp. You pull out, you go to the next tool, the servo activates, it clamps it up again, and then you pull it out. So in terms of performance, in terms of the stability, in terms of everything that you're seeing here, the way that I've been able to kind of work with Daksh has been that the tool chain sequence is pretty much the same amount that Prusa is taking on this one. And pretty much everything else is very identical in terms of, I looked at the firmware that Prusa is using, or the firmware that they actually built. They also are using the current variations on the TMC 2209 drivers. So when you actually go into dock or to pull out or to clamp and everything, they increase the current, so as to kind of get more torque to overcome any slight force or the resistance force that might be there. And then once you actually have to start printing back again, they go back to the default values. And that is what I implemented as well, even without looking at the source code and everything. I did that like 6 months back before this came out. So all of that software stuff is very similar to what they are doing and I am doing in my system. The difference is the clamping mechanism. Their clamp does not actually need to have any wires in there because it's totally mechanical. So
Yeah, it appeals to me too for that reason. Is there anything holding the tools on the XL in place? Are there magnets?
Yes.
Clamps?
Yes. So it's a mixture of two things. So let's look at the assembled one first, so to kind of figure out how the two things are kind of mating together. So these holes that you see, these are dowel pins. I'm not sure if they're magnetized. They might be. So there are three for a triple point alignment system, the kinematic coupling. So this is one, this is second, and this is third. And then they have the clamps in here.
So I can see 4 vertical rods on the top and the right, and I can see horizontal rods on the left. That's kind of an interesting choice.
That's what I thought as well. That it essentially is, normally you would actually either have the top ones to be straight and then the other ones to be slanted on a 45-degree angle. That is what I've seen up till now on the other Toolchanger clamps or even the E3D one. What they've gone with is this particular mechanism. And if you look at what they are mating this to, that's also very interesting. So this is what they're mating it to. So if you see this, um, this essentially is like a custom mating face, wherein this I think slots in between this, so it actually goes in, and then this essentially can move around a bit to adjust to the kinematic coupling to ensure repeatability. So this is what is going in here: 1, 2, and 3.
It just doesn't make sense to me, because imagine that the acorn nut or equivalent is in the bottom left of this picture, the bottom left hole.
Right.
Then because the top center one and the bottom right one are roughly parallel, I would think it could kind of twist slightly clockwise more readily than if the rods were in different directions.
It would.
You know,
I do think that it would, but I think the clamping mechanism actually gets it to um, roll around a bit to get it in place. When you kind of extend the clamps and kind of move it over, you see that it kind of gets everything to fall back in place. So what is holding the tool head in place is primarily the alignment is being ensured by these 3 holes as in a kinematic coupling with the magnetized pins. I'm not sure if this is magnetized or if this is magnetized. My guess would be these are magnetized in terms of the dowel pins, but I'm not sure. Either could be magnetized, but they have to be magnetized for it to actually kind of hold it together. And then this is the kind of the clamping phase that comes out of the tool head. So it essentially is like a steel kind of a protrusion from the tool head with a bearing in the middle, and like it looks like a 3 mm or 4 mm pin within the bearing, allowing it to rotate freely. And rotating is very important in this particular clamping, as I'll just kind of explain in a bit. But this is essentially what's happening. So there's one face here, there's another face here. And there are 2 thoughts that I have about it. If there is a spring inside or not, I am not. Initially, I thought there was a spring in there to kind of pull it back and have the force, have the clamping be kind of tight. But I don't think there's a. I think there's a spring there, but it's in another place rather than actually being in the tool head. So this essentially is just like a steel bar that actually is protruding out with a bearing in the middle, and a small pin kind of forms like a T when you look at it from the front, which gets mated in here. These 2 U-shaped sections in here. This it goes in here, and then if you look at the this is a magnet for a Hall sensor, I think, to confirm if the docking is complete and everything is tied together. So this is just a magnet that there would be a Hall effect sensor somewhere here on the tool head to detect that. So that is essentially the primary mechanism that they're using in terms of where everything goes in before the clamping actually happens. So this steel plate, I think it looks something like this in here. So when you look at this, there's this big rectangular hole here. There is a small.
I see. So they're using the lateral motion to
Yes,
do the clamping.
to do the
So the
clamping.
upper face of, here, I'll annotate, right there is pressing down on part of the pin, I assume.
Yeah. So what
And
happens
in the
is
back,
that-
it's rolling.
right. So the pin actually goes in here. It goes to the back of this. And when it does the lateral motion, the pin actually comes in somewhere here to lock in this place. So the initial thing goes in here. This thing moves like this, and the pin ends up here, being locked on both the top and the bottom clamps. And the way that they ensure the lock clamping mechanism or the lock rigidity is using springs. And they're using springs very, very intelligently. So if you look at the assembly that they're doing, these are the two faces, the clampings. Okay. They want these two holes will mate against the belt, the belt clamp. So they will actually go in like this. So there is those two holes will go somewhere in here. They would actually be clamping in here. Or they would actually be resting in there. So this actually goes in like that. So this is the aluminum piece riding on the belt or the carriage. And this screws in here on top, and there's another one that actually screws in the bottom. What they're doing is that when you're installing it, they want you to put in springs and some guides in these holes, which will be mating with the aluminum piece riding on the carriage.
I
Now
got it. That pushes on the pin
that pushes on
pin
the
holder.
on the plate. Yeah, that pushes on the plate. These pins and the springs actually are pushing on this face of the plate here. And what they're essentially doing again is, if you look at these two screws that are coming out, what this is essentially is interestingly, this is a silicone piece to help the plate glide without any friction. This screw is sitting somewhere in a divot here, and there's a spring that actually is in between the screw head and the silicone face. Then there is this spring that actually is pressing down from here. So what this spring is doing is, this is when you actually clamp everything together, this pushes the plate down, but there is an opposing force from this side as well, which is riding on this particular screw or the bolt. And if you look at the mating surface, these bolts, they are going into blind joints. They are not actually being screwed in. They essentially are going into blind joints here. Screws actually come in from the front onto these threads. So these are not getting screwed in anywhere. They're just going into a blind hole that allows it to move, that allows the screw to move. So essentially what is happening is that the face of this bolt is sitting below this silicone wiper here, or the silicone piece here. So there is a bolt that is standing upright. There goes a small spring, then goes a silicone wiper or a silicone piece, and then comes the plate, and the bolt actually protrudes towards the top. Now, what happens is that there are two opposing forces that actually are keeping this tight, this plate tight. The idea is to keep this plate tight. There's one that is coming in from this spring from the front, and there's another one that actually is coming from the spring on the back. So when that rolling pin actually comes in here, the tolerances are such that when this thing starts moving, it rolls the pin along with it to lock it in place. So in this one, it actually has to move this because there's a T. This whole thing opens up and forms a T here. So the pin actually has to come in somewhere here, just like this, So the pin has to come in here. Now, when the pin actually comes in here, the spring from the below the silicon piece is going to keep pushing this plate to the front. But the other one is going to keep the one from the carriage is going to push it back. So the whole joint in here, this actually is going to be tightly held in with between that T, between in this place in here, because of the fact that this is very tightly being fit in place, and the spring act and the rolling pin essentially is kind of just pushing it just a bit to lock it in place. That's what's happening here. So they're not using like the initial design that everyone thought was that I think there's going to be a groove here somewhere that actually locks in that pin so that it cannot move or stuff. I don't think that is happening here. It's just that tension from both the sides that actually is keeping the whole thing in place. Thoughts?
Yeah, I don't fully understand. Like, it would twist slightly if it has a spring pushing on one side and then pushing on the other from the opposite direction. I understand how the silvery set screw things, those are constraining motion.
Yep.
So we have a nice slider, right? It moves in this direction. And we have constrained mostly up-down motion with springs that are hopefully pushing it to one direction and breaking the preloading it to avoid flop or backlash there.
Exactly.
The thing that's a little hard to visualize is when the pin with the protrusion, or the rotating pin with the protrusion,
Yep.
slides in here, how that leads to a grabbing motion as the tool head, as the gantry slides.
So just think about it in this way. Let me see. So this is what they're pulling with. So there's when this is going to get pulled with the tool changer, there is a rod that actually is going to slip into something like this. Let me see if I can find a pen. Where is...
Yeah, that whole thing has to lock and unlock.
So this is what, this essentially is what gets pulled to this side. Okay, to lock. This is a T. So just think about it as a T that actually is opening up like this. So this essentially is something like this.
I got you. Okay, I understand now. So that right side hits a pin.
So
the gantry moves an X,
so the pin,
and then it
pin comes in
locks
here.
as the pin rolls
pin,
along the
right,
edge.
The pin gets locked here with the two springs, the two side springs actually keeping it in place. The other locking is being done by the magnets to actually keep it in place in a certain way. The final locking actually is being done, that kinematic coupling is what essentially is doing the initial clamping in terms of that this is where it needs to sit. And then the eventual final clamping happens here. Now, there is a spring that actually is pushing down like this. There's another spring that actually is coming up like this. I'm not sure if that spring is here or that spring is there. It might be on both ends because I haven't looked at it internally. But these are the two opposing springs that are actually causing this to be tight. When you actually, if you look at a video, I think there are a couple of assembly videos that are out there. Initially, when this comes out, this is all flopping around. This metal is just kind of clanking in there. It is not held with anything. So it cannot move out because of this screw being in there. But it is not as if it is preloaded or anything. The preloading is happening because of the spring that actually goes in here. So they're actually adding a spring in here with that guide that is essentially allowing it to be clamped down. And this is essentially the pin from the protrusion that actually kind of moves in here. So this is going to move to this side and it gets locked in here on both the top and the bottom. When it needs to unlock, they again put a rod in here and push it to the other side. So what happens is that this actually rolls in here, and then it can actually come out.
Yeah, so that makes sense. I don't think they need more than this 4 springs that they add. I
Yeah.
don't think it needs one on the other side because you've got 2 springs pushing on a plate, and that's gonna, especially when combined with the rolling
Right.
pin doing the grab, it's gonna lock.
Exactly. That's what the whole thing is. I don't think there is, because the pin essentially is the bearing in that they actually put it into this. Wait a second here. How do I turn this off? Rotate. So that pin or the protrusion essentially has a bearing in it, and that essentially allows the pin to rotate a bit.
The bearing's clever. I've never seen this mechanism. It's like a combination of a kinematic coupling and a rolling locking pin.
Exactly, and initially when that this whole thing came out, I don't have the design now, but I did do a similar design wherein I actually also used a bearing in between with the pin to get the rolling motion in. But that design essentially kind of envisioned that there was a something that was actually pulling this out to lock things in place. So the if it had to be pulled out, there would have to be an incline that actually goes on this particular strip. There would have to be an incline, then that kind of goes into a locking divot or something like that. But what they essentially are doing is turning it around. The tension is coming from the block itself. It's not coming in from the tool. So there's no spring or anything that actually is keeping things in here. It is just the um, the forces in this particular block that actually are allowing it to be tightly coupled.
Right. It's the spring force of the springs pressing against the metal, and the metal is pressing against the rolling pin, and that constrains it in the Y direction. So what's clever is using the X motion to trigger Y locking.
Exactly.
And they're doing that in almost the width of the tool head, but they're adding just a centimeter or so.
Yeah, I think it's about 10 mm or 10 or 15
Yeah,
mm actually is being
10,
moved.
something like that.
Yeah. So this is pretty interesting. It actually is pretty
It's compact.
It is very compact. It's very compact.
Eh.
Does not need a servo or anything. And for something like a small tool changer, the kind of one that you're envisioning, having 2 tool heads on the side of the Z extrusion, or 2, I think you should be able to accommodate 2 tool heads on either side of a normal V0, I would think. So the Z extrusion that actually the Z rail rides on, there can be one on left side, one on the other side, and then you can just pick and choose.
Cool. Yeah. So I guess this requires accurate CNC metal plates.
See,
I think
we could do it in 3D printing, but I think so. I have an idea about this as to what to use to actually do this. You could use internal clamps that are there. So a second here. 2020. But the difficulty would be to actually get a bearing in there. We have to come up with something else that actually kind of does that. 2020 extrusion, and then connectors, something like this. So it has pretty much the same thing. You could actually drill this out, have like a 4 mm double pin actually going in there, constrained by 2 shims um, on top and bottom, but the rolling motion will not be constrained. it will not actually be very similar to what a bearing would be. It will still roll, but that is the only thing that I can find that off the shelf that looks anything like this.
If you go back to that bracket, there is one way, which is you can buy spring-loaded, ball-bearinged set screws. And I know on some Doom Cubes, people were using them as really nice latches
Nice.
that would hold things in place, and that would give something similar. It's rolling motion,
Okay.
and it would fit in a threaded hole,
And it holds. Nice.
and it would provide, the spring force to retain in our case, in the Y direction to provide tool head locking.
Yeah.
That's the only thing I can think of. I mean, it's kind of a complex design. You've got CNC machine blocks, you've got maybe stamped metal plates, and then you've got the bearing protrusion thing, which is a machine component. So you're looking at least 4 unique machine components. Then there's a 5th on the right side, whatever the hell that thing is that holds the pin. I don't know that thing necessarily needs to be as accurate, so maybe that's printable.
Yeah, this
But at least 4 of those
this
things.
is easily printable. They're using a lot of Hall sensors to kind of, so you see a magnet here. These 2 pins actually go in here. These are like I think PTFE block holes guides or something like that. So these 2 actually go in here, and then these are the locking pins. There's a magnet here, there's a magnet here. These are to clamp it up. And then this magnet is for the Hall sensor to kind of detect when the tool head has been clamped. This thing in here I'll look into what you mentioned, but this can actually come out of this, which is like an off-the-shelf component. The bigger issue is this thing in here. See, you could do this with 3D printed parts. I think you could do it with 3D printed parts. If you have this plate, which essentially is the force is going to come onto this particular plate, because the rolling pin is going to glide on this, and it's going to push on this also, as the tool head gets locked, because this metal part is going to push on this particular, is going to pull on this plate. It's going to pull out, trying to get out of that particular lock that is there from here. But given the magnets that are in place on the 3 kinematic coupling, how much force that is going to be is something that needs to be checked. I don't think it's going to be that much, because the magnets anyways are pulling in the opposite direction as this particular pin, which is trying to get out. The magnets are trying to hold it in, the whole block in. Because there are 3 magnets that actually are going to keep that tool in place here. This pin is going to try to pull it out. These 3 magnets are going to try to put it in. So I do think you can do this with 3D printed parts, and it might actually just work. The issue for me is that if I go this route, I'll have to kind of redesign the whole docking mechanism as well. Because mine actually goes in laterally in and laterally out. There's no horizontal motion in the Y. Mine only goes in X. Mine only goes in Y, comes out in Y. There's no X motion involved with my tool changer, because of the fact that the servo is the one that actually is doing the clamping. I would not be able to fit 6 heads in. That is one thing. I'll have to lose at least 1 head to allow for that lateral motion or the X motion to be in there. And I have a way of kind of making mine wireless as it is. I am adding connectors. Everything is, I'm moving to the tool head, and I'm using pogo connectors to pass the power from the tool head, power and the signal to the servo from the tool head itself. So if I can actually make this wireless on the current system that I have, it's just too much of a hassle for me to actually kind of just go this route. But for someone who's developing something from scratch in a limited space with a compact tool head, I think this one makes perfect sense for you guys.
Yeah, it's probably a good spot. Or actually, if you want to click, I sent a link for what I was describing in the chat for Zoom.
In chat for Zoom. Okay, let me just check. Okay, interesting.
And I haven't even looked at the size of that one, but it's pretty big. But something like that kind of matches what we're looking for of to one degree, which is something that gives rolling friction and applies spring force.
Yep.
And in our case here, it's very simple to mount. You use a slotted screw on the back side and you just screw it in. And then you get adjustability as well for tension. And they're cheap. So it has a lot of desirable properties.
Interesting. So this essentially is, where do you envision mounting this? On the tool or on the clamping mechanism? This is the tool one, right?
Yeah, I would envision this pointed against the
This,
shiny plate. So it'd be a different orientation than you see there. It would be 90 degrees shifted. It would be pointing in the Y.
okay,
So it'd have to be, you'd poke it through, and then as it rolled along, it would apply the pressure on the metal plate.
understood. Yep. Right, because there's the spring loaded in there that actually is going to provide that tension that we need.
And I'm sure there are other ways to do it. This is just the simplest one that comes in mind in terms of, drill hole and screw and thing. All right. Was that what you wanted to show in terms of kind of how the Prusa Toolchanger works?
Yep.
Maybe you want to hit stop the recording and we can chat about the good stuff.
Sure. Just give me a second here. I'm going to send you another link in a private chat because I think this is going to expire in 2 minutes.
Sure.
So give me a second. I'll send you another link and then we can actually kind of connect back again.
You can also join on Discord as well.
Yeah, either way is fine. Let's do Discord.
Okay. See you there.
Okay. Thank you. Bye.